Welcome to the deep dive. Today we are examining a crisis that affects potentially up to a quarter of the global population. This lack of reliable access to, well, food, water, and energy.
Yeah, and the numbers are pretty stark. You mentioned 821 million facing hunger back in 2017. Malnutrition, a factor in nearly half of infant deaths. It's huge.
It really is. And traditionally, when we talk solutions, it feels like they're discussed in separate boxes, right? Energy transitions over here, food production over there.
Exactly. Academia, has often treated these as these kind of isolated challenges. But the scale of global insecurity really demands a more systemic approach.
Right.
And this study we're diving into today, it sort of breaks that mold. It proposes a completely integrated, almost symbiotic solution, linking energy infrastructure directly to sustainable food and water.
That integrated approach, that's really the core of what we want to unpack today. Our mission, really, is to explore the findings of the study, integration of greenhouse agriculture to the energy infrastructure as an elementary solution. It models a path that could cover basic vegetable intake for, well, billions.
Mm-hmm. And to really grasp the efficiency gains here, you first have to understand the sheer scale of the current problem with traditional agriculture.
Okay.
It's incredibly resource intensive. I mean, think about this. It occupies 40% of all non-ice covered land on Earth. 40%.
Wow, that much.
Yeah. And it uses 70% of all human water consumption. 70%. And even with all that, we still need to expand agriculture just to meet, current and future demand.
Okay, so that sets the stage. Let's look at the pivot point this study proposes. They're basically shifting agriculture from the open field into these highly controlled environments. They call them container-sized agricultural units, or CSAUs.
Right. We're talking about taking standard shipping containers and turning them into these high-tech sealed vertical farms.
So what are the big advantages?
Well, the benefits are pretty compelling. A CSAU, it needs only about 2% to 5% of the water that traditional open field methods use for the same crops.
2 to 5%, huge water saving.
Massive. And because the environment's controlled, sealed off, there's no need for pesticides or herbicides. That takes a lot of pressure off the local ecology.
Okay, no pesticides. That's significant.
And then there's the land use.
Yeah.
A single 30 square meter CSAU can replace 204 square meters of open field. And because they're containers, you can stack them.
Stackable, right?
Up to 5 high, they reckon. So one small footprint replaces over 1,000 square meters of, conventional farmland.
That land efficiency is really clear. Okay, but what about the output? Let's define what success looks like in terms of actual nutrition. What are these units trying to deliver?
Good question. So the World Health Organization, the WHO, they recommend about 146 kilograms of fruits and vegetables per person per year. That's about 400 grams a day. Now, to make the modeling manageable, the researchers defined a metric called the VGY unit. That stands for Vegetable Equivalent Yearly.
VEGY, okay.
When one VEGY represents 76 kilograms per person per year. So basically, it's half of the WHO fruit and veg recommendation, but focused just on the vegetable component.
Got it. Half the WHO target vegetables only. So using that VEGY metric, how much impact can one of these 30 square meter containers actually have?
Well, based on their optimized yield calculations, they looked at 5 main crop groups: tomatoes, cucumber, roots, leafy greens and herbs, and lettuce. A single standard CSAU can produce 42.6 VEGYs.
42.6. So in real terms.
In practical terms, one container provides that recommended annual vegetable portion for 42.6 people per year per container. The production potential is, well, it's outstanding.
Okay, this is sounding almost revolutionary, but let's talk about the elephant in the room, the hidden cost. Creating that hyper-efficient environment must take a lot of energy, right? What's the bottleneck?
You nailed it. The energy cost is the critical bottleneck, and it is immense.
How immense?
A single CSAU needs 125 kilowatt hours per day.
Per day.
Wow. That works out to over 45,000 kilowatt hours per year. And that's like at least 4 times the energy required by other controlled environment agriculture methods people have reported.
Okay, 4 times more. That's huge. Historically, that kind of cost would just kill the idea at scale, wouldn't it?
Absolutely. It's made these units too expensive to run commercially in most places.
Right. And this is where the study's integration idea really flips the script, as you said earlier. They figured out the real cost isn't necessarily generating the power.
Exactly. It's the logistics. It's getting the power from the plant to the user.
So they propose putting the CSAUs right next to the power generation source. Why does that help so much?
Because globally, when you look at your electricity bill, the cost of actually generating the power is often less than half the final price.
Yeah.
Here, they say it's by 44%.
Only 44%, so the rest is...
The other 56%,
Oh.
that's taxes, transmission costs, distribution costs,
Mm-hmm.
all the stuff involved in getting the electricity from the plant through the grid to your building.
Ah, okay.
So, if your CSAU is physically right next door to the power plant, coupled directly to the generator, you can potentially bypass most of that 56% overhead.
Making the high energy demand suddenly much more affordable.
Precisely. Suddenly, it becomes potentially commercially viable. By solving the energy delivery problem, they solve the economic problem of farming in a container.
I do appreciate the elegance of that cost avoidance, but let's be realistic for a moment. We're talking about putting potentially millions of these farm units right next to power plants, sometimes, like in your case 3, maybe in dense cities. Doesn't that create, huge security issues, zoning problems, co-locating critical food supply with critical power infrastructure?
That's a really important point, and the study does acknowledge it. They frame this co-location as a necessary trade-off, but one that's very dependent on the region. Their argument is basically that in those really land-scarce, crowded places where you most need secure local food, the benefits of having the food source right there, powered efficiently, might outweigh the risks, provided, of course, you expand existing infrastructure security protocols to cover the food units too.
So enhanced security is part of the plan?
Yes, and look at it from the power plant's perspective too. The CSAU becomes a stable, predictable, local customer for its electricity. Plus, as we'll see, it can often use the plant's waste products, like heat and CO2.
Turning waste into an asset.
Exactly. That infrastructure connection, that symbiosis, is really fundamental to the 3 specific integration models they propose for different global situations.
Okay, let's walk through those. How do these regional models work?
So, Case 1 is designed for extreme cold weather regions. Think places like Canada, the Nordics, short growing seasons, often plenty of biomass resources. Here, the idea is to couple the CSAU system with a biomass, or maybe a biogas power plant. The CSAU uses the waste heat from the power plant. That's crucial for keeping the container warm enough for crops when it's freezing outside.
Using waste heat makes sense.
And even more cleverly, it captures CO2 emissions directly from the power plant's exhaust. They pump this into the CSAU, boosting the CO2 level inside from the normal, say, 400 parts per million up to around 700 ppm.
And that helps the plants.
Oh yeah. That CO2 enrichment can increase crop yields by up to 60%, according to the study.
60%, wow. So you're using waste heat, capturing CO2, boosting yields.
And potentially, the biowaste from the CSAU itself, stems, roots, unusable leaves, could even be fed back into the biogas plant as fuel, aiming for a kind of carbon neutrality.
Okay, that's a really neat cycle. What about places where water is the big issue?
That brings us to Case 2, water scarcity. Think North Africa, the Persian Gulf, places like that.
Very dry regions.
Exactly. Here, the energy sources are more likely to be solar PV and wind, probably balanced with battery storage. But the main benefit they're exploiting is this CSAU's incredible water efficiency.
That 95 to 98% saving we talked about.
Precisely. If your main source of fresh water is desalination, which is itself very expensive and energy intensive, saving 98% of the water needed for agriculture is, well, it's a game changer.
Absolutely critical in those regions. And the CO2.
The CO2 could be captured directly from the air, which is getting more feasible, or maybe from nearby industrial sources if available, like a cement plant releasing CO2.
Okay. And the third case, maximizing efficiency in crowded areas.
Yep, Case 3 focuses on land scarcity, places like Japan, South Korea, maybe dense megacities elsewhere.
Where space is at a premium.
Exactly. This model really leans into the high yield per square meter and that stackability factor the CSAUs. It allows them to fit into tight urban environments, maybe on rooftops, perhaps even underground.
Underground farms, okay.
And they could be coupled with things like municipal waste-to-energy plants, which are often located in or near cities anyway, or other local power sources for both electricity and maybe CO2. It shows the concept could work even where land is incredibly valuable.
Right, adapting to the local constraints. Okay, so those are the regional models. Let's zoom back out to the global picture. The study projected forward to 2050, based on what seems like a fairly modest energy commitment.
Yeah, the main assumption for their 2050 projection was dedicating just 5%, only 5% of the projected electricity generation from 4 key renewable sources.
Which sources were those?
Biomass, waste-to-energy, solar PV, and wind. So just 5% of the output from those specific renewables by 2050.
And what does that 5% buy us? in terms of feeding people?
The results they calculated are pretty striking. Dedicating that 5% could power about 55.4 million CSAUs globally.
55 million containers.
And that number of units could provide the necessary vegetable intake, that VEGY unit we defined, to 24.4% of the projected global population by 2050.
24%. That's nearly a quarter of the world's population in 2050.
Yeah, it works out to about 2.36 billion people having their recommended vegetable intake potentially covered by this system.
That's huge impact from 5% of renewables. What about the total energy cost?
The study concluded that the total global energy investment needed for this massive agricultural shift is only about 3.6% of the total projected global electricity production for 2050. Not just renewables, but all electricity.
So less than 4% of total global electricity could potentially solve the vegetable needs for almost 25% of the population. That sounds like an incredibly efficient trade-off.
It really does. They even calculated an efficiency metric, the VEGY coverage per unit of energy invested. Globally, they found that for every 1% of total energy generated that you invest each year into this CSAU system, you cover the VEGY demand for 6.8% of the global population. So a small energy input yields a really significant nutritional return.
That's a powerful ratio, and presumably this investment also takes a lot of pressure off the environment, off traditional farmland.
Absolutely. The total amount of traditional open field farmland that would be liberated or freed up under this scenario globally is calculated at 9,635.6 square kilometers.
9,500 square kilometers. How big is that?
Slightly larger than the island of Cyprus, for comparison.
Okay.
And when you think about all the competing demands for land use, housing, conservation, other industries, especially in really crowded regions like China, India, Japan, reducing the agricultural footprint by that much is a major ecological benefit.
Beyond just the land, there's the water security aspect too, right?
Definitely. By switching this portion of vegetable production to CSAUs, the system saves at least 14,545 million cubic meters of water globally every year compared to traditional methods.
14.5 billion cubic meters of water saved.
Yeah. And crucially, remember the pesticide point. By eliminating the need for pesticides and herbicides in these millions of production units, we significantly reduce the chemical load on the environment. This could really help protect vital pollinating insect populations, which, something like 75% of our food crops depend on.
Okay, the environmental benefits stack up alongside the nutritional ones. But let's circle back to those 55 million units. That is a massive number of containers. It sounds like a colossal industrial undertaking, especially if each one has a high capital cost initially. Are we really confident the world can make or repurpose that many units? And who pays that initial $85,000 per container cost they mentioned?
That's fair. The scale is daunting. But the feasibility argument in this study is actually one of its more compelling aspects, I think.
How so?
They point out that while 55.4 million sounds futuristic, the global inventory of actual shipping containers back in 2015 was already 37.6 million.
Okay, so a lot exist already.
Yeah, and here's the kicker. They estimate that a staggering 62% of those existing containers are typically idle at any given time.
62% are just sitting there. Why?
Mostly because it's expensive to reposition empty containers around the world to where they're next needed. Trade imbalances mean they pile up in some places and are scarce in others.
Ah, okay, so there's a huge pool of unused assets.
Exactly. So the idea of repurposing these existing idle containers becomes really powerful. It's potentially a massive economic and logistical win-win. You address the food security need and you solve a major headache for the global shipping and logistics industry by giving those idle containers a new, valuable purpose.
So we're not just building millions of new boxes, we're potentially activating stranded assets that already exist. That changes the picture significantly.
It really does.
Yeah.
Now, regarding the cost, yes, that initial commercial estimate of $85,000 per unit is high, but the study anticipates what usually happens with new technology.
The cost curve comes down.
Right. With bulk production, standardized manufacturing processes, and likely some government involvement or incentives to drive demand, that cost is projected to drop significantly over time, making the whole system much more scalable globally.
Okay, that makes sense. So to quickly summarize this groundbreaking work, by investing just about 3.6% of future global electricity generation into this integrated, controlled agriculture system, the world could potentially secure the basic recommended vegetable intake for nearly a quarter of its projected population by 2050.
It presents an almost unprecedented potential return on investment for global health, food security, and environmental sustainability, all linked together.
It really is quite something. Now, here's a final provocative thought for you, the listener, to maybe carry forward from this. This study focused purely on covering the vegetable intake, the VEGYs. Important, but only part of the picture.
True.
But imagine a future where this kind of CSAU technology, this integrated energy ag model, is combined with other emerging research. Specifically, I'm thinking about technologies being developed right now to create direct protein, maybe from energy and air, or perhaps high-yield protein from things like algae cultivated in similar controlled systems. If you could combine those integrating energy, water, vegetables, and protein production within a single, distributed, efficient framework, could that combination finally bridge the entire alimentary gap? Could it fundamentally change what food security means for everyone on the planet? Something to think about.
A truly integrated approach across all nutritional needs.
Yeah, that's the long-term vision, isn't it?
That was our deep dive into the findings of integration of greenhouse agriculture to the energy infrastructure as an elementary solution. Thanks for joining us. We'll see you next time on The Deep Dive.